Good morning, everybody, and welcome to week 6 of the Certified Water Specialist Water Treatment Fundamentals course, the certification course. This is week 6 out of 15 weeks, and we're a little over a third of the way through. That's pretty impressive, wasn't it, how I did that right in my head, like I calculated. What I did is I took 15 and I divided it by 3, and that's 5. And since we're on week 6 now, I was like able to calculate that we were over a third of the way through. That's pretty impressive. I know you guys are like, wow. Okay, so anyway, let's get started. Today we're going to be talking a little bit more about the ion exchange process and more on anion exchange, but it's follow-up on last week. Okay, so first and foremost, I always want to say thank you. I definitely appreciate the opportunity to serve you guys, and it is always my goal to make sure that the information that I give to you is at least as valuable as the time you're giving to me. I do appreciate it very much. What we're going to talk about today, other stuff that can be done with ion exchange other than just water softening. We talked about that last week, water softening mostly. Today we're going to talk about other stuff. We're going to talk some about salt and brine, some stuff about resin, and let's get started. Okay, so there's dealkalization. That whole bicarbonate hardness thing keeps coming back up. Remember, we talked about that the last couple of weeks in the chemistry and last week when we talked about hardness. So let's review a little bit because I'm kind of thinking that might be important to our industry, the whole bicarbonate hardness thing. I don't know. Hardness, really, in this industry? But okay, let's do it anyway. So let's do a little review. So what happens is water, as part of the hydrologic cycle, the water evaporates, it goes up into the atmosphere, and amongst other things, it collects carbon dioxide up there. And when it collects carbon dioxide, it forms this acid called carbonic acid. And when that falls down to the ground, it dissolves the rock that's in the ground, the calcium carbonate or the CaCO3, and it dissolves it. And when it dissolves it, then it becomes calcium bicarbonate. So calcium bicarbonate is dissolved hardness. When the water heats up, the carbon dioxide leaves the water and causes the reformation of CaCO3 or scale buildup. So after the water is heated, we get scale in the form of calcium carbonate, and we also get free carbon dioxide. Carbon dioxide can create serious corrosion problems with boilers and piping systems. Softening will reduce the scale, but it won't take out the corrosion. Just so you know, this is important, softened water does not cause corrosion. It does not cause corrosion. Softened water does not cause corrosion. Softening will save on the heating and maintenance costs with the boiler system, but since it replaces the calcium, magnesium with sodium, it has basically the same total dissolved solid. So this is kind of important to know, is that a water softener doesn't reduce the total dissolved solid count. Remember, the process is referred to as ion exchange. It's not ion replacement or ion removal. It's ion exchange. That means that you're removing the calcium and magnesium, but you're replacing it with sodium or potassium. So it's going to have basically the same TDS. In fact, the TDS may even be a little higher because of the size and the equivalent molecular weights of the sodium or potassium. I saw a Mythbusters episode. I got to mention this, by the way. I was watching a Mythbusters episode on Netflix the other night, and they actually, do you know that pure sodium or pure potassium is it's highly explosive and reactive to in water? It was kind of cool. They were testing the myths of MacGyver, and there was an episode of MacGyver apparently where he escaped out of a prison, out of a jail, where by taking a piece of sodium and putting it in water, and he blew a hole into a concrete wall. So they checked that to see if the explosive capabilities of the sodium would actually blow through a concrete wall, and they couldn't do it. They ended up having to use C4 to blow up the concrete wall, which is always fun. Mythbusters rock. But anyway, it was very cool. Since I've gone on and looked at some YouTube videos and stuff like that of reactions of potassium and sodium in pure water, it's pretty cool. Anyway, it just made me think of that because the sodium, we think about sodium when we think about it being in the water and salt and stuff, but when you put it in its pure form, it's a lot different than table salt, that's for sure. So anyway, so water with that softened water that's had the calcium, magnesium removed, it's replaced that with sodium or potassium, it keeps the same amount of alkalinity and the same amount of CO2, carbon dioxide as well. So to further reduce energy cost and save a boiler system, we should get rid of or reduce the total dissolved solids. That's called dealkalization or deionization. If you get rid of the total dissolved solids, you can save 24 to 45% energy over just chemical treatment if you get rid of it entirely. Alkalinity, the definition of alkalinity is the capacity of water to neutralize acids. The capacity is caused by the water's water's content of bicarbonate, carbonate, hydroxide, and occasionally borate, silicate, and phosphate. Alkalinity is expressed in parts per million of equivalent calcium carbonate. Alkalinity is not the same as pH because water doesn't have to have a high pH to have a high alkalinity. Alkalinity is a measure of how much acid can be added to a liquid without causing a great change in the pH. And this is kind of gets into some of the alkalinity stuff. Just to kind of explain I think when we hear about these alkalinity systems, the Kangen units and all that stuff, I think that the focus is on the higher pHs. But it's important to understand that alkalinity doesn't really have as much to do with the pH as it has to do with how much acid can be added without causing a great change in the pH. Alkalinity treatment, there's chemical. This is, in this, when we talk about it, when the books talk about this stuff in terms of water treatment, we talk about it in terms of lowering the alkalinity, bringing it closer to neutral because things tend to work better when the water is pretty close to neutral. So to treat alkalinity, we treat it with chemicals. We can use chemicals to control the alkalinity. The book talks a little bit about something called the split stream process and a weak acid cation method. It requires the use of acids and extra precautions. I'm not going to cover that a lot in this webinar. The test doesn't go over it a lot either, but it is worthy of reading. I would read up on that if I were you, just to have the knowledge. Strong base anion resin, and that's the simplest way to remove to treat it. It's the opposite of a strong acid cation, which is what water softening does. And it's most commonly used in smaller installations. And you don't have to handle the acids with it. It uses salt and caustic soda for pH stabilization. Silica, if there's silica in the water, it can impact treatment of other contaminants like arsenic. So silica causes a really, really hard scale. It's going to be really hard on reverse osmosis membranes. Also, boiler systems can cause a big problem. In residential world, only if some of the arsenic medias that are out there, some of the specialty medias that are there, silica can have an impact on it. But typically, it doesn't have, on residential water treatment, it's not going to have a big impact. You can remove it with a strong base anion resin. That's regenerated with hydroxyl, and it creates sodium hydroxide, which is very alkaline and has to be neutralized with an acid. Like I said, it's hard on reverse osmosis membrane. Okay, so let me back up here a little bit and explain what we're talking about here. Okay, when I talk about a strong base anion resin as opposed to a strong acid cation resin, think about this. Basically what you're doing is a cation resin removes cations. It carries a positive charge, it carries a negative charge and removes positively charged ions. Okay, so a cation resin removes cations. It removes positively charged ions. What we're talking about mostly today here is an anion resin that's going to remove the negatively charged ions. If it's an anion resin and it's removing anions, we know that the resin itself has to have a positive charge to it so that it can take out the negatively charged ions in the water. That's what we're talking about when we're talking about removing silica or when we're talking about removing nitrates here. Okay, those are anions. Those are anions, and you can put an anion resin in it that will take it out. Okay. Just so you know, anion resin can sometimes have a fishy smell too. You may see that again somewhere. That if you see something, anion resin can have a fishy smell to it. Nitrates, maximum contaminant level is 10 parts per million. It causes hemoglobinemia in babies and the elderly. We talked about this earlier on. Hemoglobinemia is also known as blue baby syndrome. Nitrates have no detectable odor, taste, smell, or color. It typically comes from sewage, fertilizers, bacteria that converts ammonia to nitrate, industrial waste, etc. It can be removed by a reverse osmosis or a distiller, or you can use an anion exchange resin tank for treatment. If you have, let's say you have a water softener and so a cation unit and an anion unit next to it for nitrates, they can actually share the same brine tank because it uses regular salt to regenerate it. The anion resin does. So you can have one brine tank, one salt tank. The water softener, the cation exchange unit, will use the sodium to regenerate the resin. The anion unit, the nitrate unit, will use the chloride part to regenerate the resin. So it actually uses the same brine. It just uses a different component of the sodium chloride to regenerate. The thing is, most of the nitrate resins that are out there remove all the anions, not just the nitrates. So you got to know what's in the water due to anion selectivity. The nitrate resins that are out there will typically take out sulfates first, then nitrates, then chlorides, then bicarbonates. So if given a choice between taking the nitrates out, if you've got a lot of sulfates in the water, then you're going to have a hard time removing the nitrates because the resin's going to choose to take out the sulfates first. There are nitrate selective resins, but they're way more expensive. And if you have other things in the water, or if you're not regenerating it often enough, then you can get nitrate dumping. That means that even some of the nitrates may stick to that resin, but if you have sulfates coming in after it, then it's going to kick that nitrate off, and the nitrate's going to go on into the water. You do have to be careful about the bed. You need more contact time with an anion resin, so you want a deeper bed, and you need to be aware of the brine discharge and where that's going because you don't want to put the nitrates back into the ground again. It's best to use potassium chloride with a nitrate removal system if you're draining to a septic tank. Uranium is naturally occurring, it's radioactive, and it can be removed with a type 2 high porosity strong base anion resin. So you can take out some radioactive contaminants with resin. It uses regular salt just like in a nitrate system. So let's talk a little bit about salt. Yay, salt! Okay, it's best to use a high quality sodium chloride when you're brining, when you're regenerating. Vacuum salt, that's the stuff that looks like peanut brittle, you know, so basically they form it and then drop it and it shatters. By the way, this is a little plug for the MV Pro Call. If you go to my website and you look at the upcoming seminars page and you go to the MV Pro Call page, the MV Pro conference call, we have a recording of a salt expert who did a great job in explaining how salt was made and why you get that gray stuff in using some salts in a brine tank, and he talked about vacuum salt and solar salt it's a great half hour. I strongly recommend that you go listen to it if you want to learn a little bit more about salt. And that's on the website as an MP3, so you can download it and learn a lot more about it there. But vacuum or solar salt's the best. It's usually about 99% pure. Stay away from rock salt because it tends to have debris and sediment and all kinds of crap in it. And tends only to be about 94% to 99% pure. If you are going to use rock salt, then you need to use Louisiana rock salt. That's the best stuff that's out there. Potassium chloride, by the way, is about 98% pure. And anytime you're making brine, it's best, and this is going to be a difference between some of your less expensive water conditioners and your more expensive ones. It's best if you can use soft water to make the brine. Sodium chloride, temperature does affect saturation. It's best at 60 degrees. So in your maximum saturation, salt saturation is going to be 26.4%. Salt water does freeze at 14 degrees. That's why if you live in a really cold climate and it gets below 14 degrees, salt doesn't work on the roads either. It doesn't work very well because it will freeze at 14 degrees. 1 gallon of saturated brine weighs about 10 pounds. And there's the salt equivalents per inch of saturated brine draw, and you're not going to need to memorize any of this. The chart is in the book, though, for you to refer back to it and reference to at your convenience. Okay. Full strength brining is usually 26%. It does not harm the resin. It does act as a bacteriostat, so bacteria can't live in the full strength or in a full strength brine. It's best if you're taking out metals like barium or iron, manganese, as well as some other heavy metals. Most water softeners operate at a 10 to 14% brine strength. You can use alternative regenerants like other sodium. I mean, theoretically, you can use alternative regenerants. Other sodium compounds are not usually used because they don't make a strong enough concentration. For example, sodium bicarbonate or baking soda. They add contaminants to the water like sodium nitrates. Not cost effective like sodium citrate. But one alternative regenerant we do use is potassium chloride. And potassium chloride was originally used in China because of high salt taxes. It's used as a non-sodium salt substitute in food processing, and it works using the same process as sodium chloride. Remember, and we talked about this before when we talked about on the periodic chart of the elements, anything in the same vertical line on that periodic chart of the elements carries the same chemical properties as anything else in that same vertical line. So sodium and potassium are right next to each other. It is 3 to 4 times more expensive than regular sodium chloride, and it's about 27% less efficient at low salting levels. That means 5 pounds or less. Once you get up over 5 pounds, then it equals out. The salting efficiencies come to be about the same. But if you're dosing the salt, if you have it set at low salt dosages, then it's going to be less efficient at the lower levels. It is good for people on low or no sodium diets. However, because the cost of potassium chloride has dramatically increased and the cost of reverse osmosis systems have dramatically decreased, it's going to be way, way less expensive to put in a reverse osmosis system than it is to use potassium chloride on a regular basis. And a reverse osmosis is going to take out not only the sodium out of the water, but pretty much everything. So, I mean, I strongly recommend, if it's an option, for people to use a reverse osmosis system in the home. Now, you can use this for irrigation, watering the grass, but again, because of the cost, it's just not going to necessarily be the most cost-effective method. It's just so daggone expensive. And watering the grass with most, if you are running it out on your lawn or whatever outside where you have rain that's going to dilute the amount of sodium in the soil, it's not going to hurt your grass. So it's not a big deal. I wouldn't stress over it in most cases. Inside the house, watering potted plants with softened water, that can be more of a problem because you don't have other water to to wash that sodium out of the soil, to dilute that sodium out of the soil. Inside plants, I'd recommend fertilizer and reverse osmosis water. It's going to do wonders for you. Potassium chloride is required in some communities, though. Here in Michigan, we run into that a lot where they require it. It's law, and they'll come around and test. They have a test well, and they'll test the soil levels and see whether or not you're using it. If the sodium levels are too high, they fine you. So in some areas, it is required by law. It bridges much easier even in dry brine tanks. Now, that's because bridging with potassium chloride is different than bridging with sodium chloride. And it's at this point that I'm going to draw a picture. Because bridging with potassium chloride is usually a hard crystallization at the bottom of the brine tank. And temperature fluctuations make it worse. So let me put on my little drawing pin here and show you what I'm talking about. Okay, so we've all heard the term bridging. So I'm going to draw a brine tank here. So I'm doing this with my mouse pad on my touch mouse pad, so that's why the lines aren't straight here. Okay, so with regular salt, all right, so you've got the float down here on this side in the brine tank. Okay, and the float may tell you, so this is the level here that the float is set on. So the float tells you the water level that's there. So you put the salt in, and the salt's all down here, and here's the water level. Okay, so the salt level is filled to about here, but down below this water level is where the salt dissolves. And so basically when you go to pull the brine in, it sucks the brine up through the brine tube and into the softener, right? Because this is where it's all making brine. But the problem is that sometimes this water level, because this is all dissolved, right? This is a 26% brine saturation down here. So really, really strong salt water. Okay. If any of the water evaporates, there's no more room in that in the water for the salt to dissolve, so it's going to reform back into its crystal because if the water's evaporated or for whatever reason it's left. So what can happen when it reforms back into a crystal is it can form this dome over the top of where that water was. Okay, and it forms a dome. It's like it's a strong salt dome. And so even if you have all this weight of salt up here, have all this weight of salt, it's not going to drop down because this dome is going to prevent that salt from dropping down into the water. So you're sucking brine, the water softener is putting the water in here, it's putting water down in here, it's making it, it's filling it up, it's going through its cycle and everything, but because this dome is preventing all that salt from dropping down into the water, basically you're bringing fresh water or water with hardly any salt brine into it when you're going through the regeneration process. And if you don't have a high enough percentage of brine in that, or salt water, if it's not making brine because the salt's not dropping down into it, then you're not going to regenerate that water softener. You're going to continually have exhausted resin in there. There's a very, very scientific way of repairing this if that happens, and it's called getting a broom handle and banging holes down through that brine solution, or rather down through the salt pile in that brine tank and breaking up this dome and letting it drop down. It's a very scientific method of doing it. A crowbar works really well too. Get that, hammer it down into it and break up that salt dome and let it drop down in there. Using a better quality salt will help prevent some of that bridging. Also, not letting that softener go more than 3 or 4 days in between regenerations. I mean, think about it. If you're only regenerating every 2 weeks, every 2 or 3 weeks, then even on city water, you put in a really large system and it's only going every 2 weeks. That allows that water to evaporate, and that's going to create that salt bridging. Okay, so you want that water softener regenerating every 2 or 3 days. Bigger is not always better when it comes to these things. Not always better. So, with potassium chloride, that's bridging with regular salt. With potassium chloride, the bridging is a little different. they still call it bridging, but it's not actually forming that salt bridge. What it does is it forms, so here's your water level, the brine tank. It's not flat. Look at that. Oh, my drawing's getting even worse. But basically, you put the salt in. Here's all the salt up here, and it drops down. But what it does, so here's your water level on the float. What it does is it forms this hardened layer down on the bottom, which gives you a false bottom of the brine tank. Okay, so it can form this hard layer down here. And that gives you the false bottom, which means that the salt's still dropping down, the potassium chloride's still dropping down, but essentially you have less water in there because the float level is still right here. That's still the height. So you can take 2 or 3 inches off the water level off there because of, and so even though the salt's dropping down there, you've got less water here because the float's still shutting it off here. So the solution here is to, a lot of times they'll put a grid plate down, which keeps the salt level up higher than what might drop down here, and that helps a little bit. But you got to, with potassium chloride, typically you got to get that thing out and clean it out every couple years, break that stuff off the bottom, and keep it cleaned out. So another way to help prevent that is to put the brine tank up off the floor. So you build a 4 to 6 inch wooden platform, and also insulate the brine tank because temperature can make a difference. Temperature fluctuations will make it worse. Insulate it above the water level. Put styrofoam between the floor and the tank bottom, and use a salt grid. And another tip is don't fill the salt tank all the way up so that you don't have the weight pressing down on it. So fill it only about halfway. Soft water brine is always a good thing. It's always a good thing to make brine with soft water. Always a good thing to make brine with soft water. And if you think about our King of the Mountain example last week when we talked about it, remember you got the calcium. It's King of the Mountain. The calcium's on that resin, and the sodium army comes in to kick that calcium off because there's so many of them. But if there are a bunch of calcium spies in with the sodium that it's bringing in to clean off the resin, then the sodium not only has to fight against the calcium on the resin, but also the calcium in the water that it's coming in with. So it takes a lot more sodium to regenerate that resin, and it's never going to get completely regenerated. So soft water brine is a good thing. Look at your competition. Look at the softener that you carry, and if probably the less expensive piece of junk, no, I'm sorry, that's not true. The less expensive, lower feature systems that are out there, they're not pieces of junk. They all have their merits, and they all they all have some value. But the less expensive systems that are out there probably do not have a soft water brine. So if yours has a soft water brine and they don't, that's something that I would use to promote your equipment. Resin cleaners. Resin can get fouled with iron, manganese, silt, hydrocarbons, organics. You can use a really strong brine solution as a resin cleaner. That helps, especially in countercurrent regeneration. It's going to help keep that resin clean. You're going to need the resin iron outs and that kind of thing less often if you have a strong brine solution using countercurrent regeneration. Lemon juice actually works because it's citric acid. It's going to redissolve that iron into its ferrous state so that it can be rinsed off. Sodium hydrosulfite or sodium bisulfite converts ferric back to ferrous. It stinks really bad. And by the way, don't mix it with bleach. So don't put bleach in a brine tank. If you're using iron out salt, it will create a toxic, hazardous gas. Hydrochloric or muriatic acid will actually bring resin back to its max capacity. So you can repair the resin and bring it back to its max capacity by using muriatic acid to regenerate. But it's also very toxic and hazardous, so it's not something that you use typically around the house. Ion exchange resin and life expectancy. Resin can break down. It can be physical or chemical or both. Anion resin is less stable than cation resin, so you typically will see some loss of life after 4 years with anion resin. Cation resin generally outlasts the hardware equipment, or 10 to 12 years. Now, I've had people comment when I say 10 to 12 years, well, I've seen water softeners with the same resin and it goes 25, 30 years. That's true. And it doesn't say that it completely breaks down or it lose all of its capacity. It just starts to lose a lot of its capacity or some of its capacity after that 10 to 12 year range. So you are going to have to set that softener up to regenerate more and more often because it is going to begin to break down. And that, my friends, is a shortened class. We actually got through this in about a half hour today. Next week, we're going to be talking about aeration and adsorption, and that's going to be live from EWQA. So I'll see some of you out there at EWQA next week. Please feel free to say hello. The rest of you, I will see you. I'll be doing it live from EWQA. Also, I'd like to invite all of you to our Thursday morning MV Pro calls. We're currently working our way through how to win friends and influence people, but it's always a great conversation every Thursday morning. Go to the website on the upcoming seminars page for details on how to log into that. And are there any questions? Any questions? Anything that I can answer for you guys? There are sample quizzes online. Please feel free to go, and we will, if there's nothing else, I will talk to you guys next week, if not before. Have an awesome weekend.